guess you already said this, but people are asking me, what are you doing in Sweden? So I have this picture to, it's an actual physical picture. On either side of me are yellow buildings that are Nordita buildings that you can't see in the picture. And they used to be hospital buildings on the outskirts of Stockholm for infectious diseases to keep people away from the city center. So my building was leprosy, then there was typhus, and recently acquired typhoid. So I'm happy to say that when I was in, it's treated by antibiotics, so don't worry. If you hang around me, it's okay. But I've stepped down from that, and instead I got a very generous grant from the Swedish Research Council, and I moved to the Stockholm University, which is the white building in the back. So they're physically right next to each other. So my life didn't change in that sense. Well, it did. I'm no longer a director. That's a very different task. But anyway, so and I spent half my year there and half my year in Michigan. But so now to the material of my talk. So let's go back 100 years to the origins of modern cosmology with Einstein's relativity in 1915. So if you think about it, throughout human history, there were creation myths for every culture, and we're in the unique position that ours is right. So we have the hot Big Bang, and it's right. If you think about that, it's just kind of mind-boggling. And I also want to point out that even at the time of Einstein's theoretical breakthroughs, still observational astronomy was barely anything at all in the sense, though that's too strong a statement. But cosmology was, on the observational side, wasn't really starting because people thought that every star that we see is part of our galaxy, the Milky Way. And they started thinking, well, maybe there are island universes and so on. But that actually only came in the 1920s with the work of Edwin Hubble. So he was using the telescopes, the Mount Wilson Observatory above the Angeles Mountains in California. And by the way, I had a sabbatical in Caltech, and you look up there, you see the mountains, you think nothing of it until you try to go up. And they have the same vertical drop as Aspen. So up at the so anyway, at the top of those mountains, for the two major advances he made, one of them is that he really showed that some things are just too far away to be inside our galaxy. And that was really the beginning of extragalactic astronomy. But going back to now to the theory side of things, it was very soon after the initial work of Einstein that people applied the equations to the universe as a whole, making some simplifying assumptions, and realized that there were three possible shapes for the universe, three possible evolutions for the universe. It could be expanding, contracting, or static. Now, Einstein really wanted a static universe because that would mean the additional symmetry of everything being, on the average, the same in time, at all times. So this was a testable question, and again, it was Edwin Hubble in 1929 who resolved this problem. He looked at atomic emissions from distant galaxies, and if you know the wavelength of the emissions, then you can compare that to the wavelength you observe here today. And what he saw was that the wavelengths between the time of emission and now, the wavelengths had been stretched. So if you threw some wave on a balloon, blew up the balloon, well, it would stretch. So the conclusion is that he concluded the universe is expanding. There's a big caveat here. We do not live on the surface of anything, okay? But the idea that wavelengths get stretched, that's what he discovered, and at that point Einstein had to abandon the idea of a static universe because it's expanding. And a simple-minded picture on you and I are not expanding apart from one another. In fact, we have a big neighboring galaxy, Andromeda, and we are going to fall in. We're going to fall together. So gravity dominates locally. But the idea is if you go to large enough scales, you see everything moving apart from everything else. So the basic idea of the Big Bang is the universe started 14 billion years ago as a hot primordial soup of fundamental particles, quarks, leptons, photons, and so forth, initially very tightly packed together, and then with time, these particles moved apart. So you started out, the universe was very hot and dense to start with, and it's been cooling and expanding ever since. We have a raisin bread model of this. Here you'd have a bunch of raisins, which are models for galaxies. And when you put the dough in the oven, the whole thing, it rises. I'm waiting to meet one person who's actually done this, but I'm sure it's true. But anyway, so the idea is that the raisins are expanding because the underlying raisin bread is expanding, not because the raisins are doing anything. So the analogy would be that galaxies are just sitting there moving apart from one another because of the underlying expansion of space. Now there's one big difference between the raisin bread and our universe, which is that the raisin bread has a center, it has a central point, but we think that the universe does not. We think that there's no special place in the universe. Certainly the Earth is not a special place, but we don't think there's any special point in the universe. So going back to this picture, if we went to a different galaxy, you'd see the same thing. You'd see on the average everything moving away from you, wherever you are in the universe. So the Big Bang is a point in time, it's not a point in space. It's not an explosion either, but let's put one everywhere if you really want to. Well, so there's been enormous progress over the last century, but even more in the last few decades. So at the turn of the last millennium, the amount that we've learned is just mind-boggling. So we got the geometry of the universe, the total mass and energy content of the universe, the age of the universe, and so on and so forth. But we still have a lot of unanswered questions. So turning to this question of the total mass and energy content, or the total geometry of the universe, this is data from the leftover light from the Big Bang, the cosmic microwave background. So this is from the Planck telescope, and what you see here are hot spots in red and blue spots in blue. The temperature of the universe is really close to 2.7 degrees Kelvin, but there are deviations that are 1 part in 10 to the 5. And it's from those deviations that we've learned this ridiculous amount about the parameters of the universe. And in particular, it's the size of the hot spots or cold spots that tells us about the shape of the universe, the geometry of the universe. So it turns out that if the universe has a flat geometry, that means there's no curvature. That means parallel lines continue on forever being parallel, as opposed to, say, the universe being on the surface of a sphere. A flat geometry, you would expect the size of those hot regions would correspond to an angular degree of this is 1 degree. And sure enough, in the data, that's where the power is maximized. That's called the Doppler peak. So the conclusion is that the geometry of the universe is flat. So that's a really astonishing statement that the fact that we've been able to resolve this question. And the geometry correlates through Einstein's equations to the total mass and energy content of the universe, and that number is 10 to the minus 29 gram per cubic centimeter. So this average mass and energy content is exactly what you need to have the flat geometry for the universe. G mu nu, the geometry, equals T mu nu, the mass and energy content of the universe, Einstein's equations. Comparing to water on Earth, here we have 1 gram per cubic centimeter. So in some sense, I guess this is what you would define as outer space. And by the way, I have a very funny story about how I tried to explain that to the Queen of Sweden. So ask me later. It got very, very embarrassing. What we get out of these microwave background measurements is a lot more information about the universe. And this is a talk in itself that I'm not giving. I'm just trying to show a few basic results. To analyze all of that data, you fit it to 6 basic parameters that are listed here. But there's a lot of other ones that you're also getting information about. But the one that I'm particularly interested in today is the amount of matter in the universe. So I'm about to show you some answers for that. But before I do, I have to mention this in this audience. WMAP is the American satellite that preceded the Planck satellite, the European one. And what do we have here? SH, the initials of Stephen Hawking. And the color code is the color scheme is just different in this picture. It's the same data, but Planck has a higher resolution. And yes, SH is still there in the Planck data. Well, so we know what the total mass and energy content is, but what is it made of? And here the answer is a little surprising. If we take everything that we're familiar with in our daily lives, our bodies and air and chairs and stars and planets, all made of atoms, all made of quarks, all of that adds up to only 5% of the universe. So I've shown that here. So 5% ordinary stuff, 25% dark matter, and 70% dark energy. Now there's something a little funny going on because WMAP got less dark matter, and then Planck is getting a bigger number, and that discrepancy is not understood. It's the same data, so there's something funny going on. It will get resolved. This dark matter problem actually goes way back about 80 years. The realization that we're missing something stems back to the 1930s, first to Knut Lundmark, Swedish astronomer, and then to Fritz Zwicky, famous, this is him, Fritz Zwicky, a Swiss astronomer, who Zwicky was looking through the same telescopes as Hubble. He was looking at the Coma cluster of galaxies, and he saw that some of them are moving really rapidly, too rapidly to be explained by the stellar material that he could see. So there's something else gravitationally pulling on these things. That was his hypothesis. Dunkle Materie, or dark matter, could be the explanation for speeding things up. And calling it dark just means it's not stars, it doesn't shine. There's no other content to the name. I have so many stories, I'm going to run out of time, but shall I tell some anyway? Okay, so in his book, he calls people spherical bastards. His colleagues are spherical bastards because they're spherical no matter what direction you look at them from. And then I was giving this radio talk show, and somebody calls in named Barbarella. Okay, it was Barbarella Zwicky, his daughter. She was bitter that nobody had listened to him about the dark matter problem. And all I had to say is, well, we're listening now. Anyway, so I guess it's true. People didn't know what to make of it. There was a lot of data, but it was really the work of Vera Rubin and Kent Ford in the 70s that nailed it as a problem that we have to listen to. And so what they did was look at rotation curves of galaxies. In other words, if this is the center of a galaxy, and you observe something moving around in some orbit at some distance r away from the center, then the speed of the orbit is determined by virial theorem. So it's the mass interior to that radius r that tells you how fast that orbit should be. And it's the same phenomenon as before. You're not getting what you expect based on the stellar light. Starting out at the center of the galaxy and moving out, if you look at the speeds of things, based on the stars that we know about, this is what you would expect. But this is what the observations show, a flat rotation curve. So you have to add in additional dark matter, that solves the problem. Looking at our galaxy, the Milky Way, at the center is a supermassive black hole that weighs 4 million times as much as the sun. Then you have this pinwheel where all the stars are, including our sun. Now you take that on its side, we call it the disk, and here's the sun. It's 8 kiloparsecs away from the center, or 25,000 light years, completely unaffected by the black hole. But that is nothing. So doing an artist's rendition of the whole galaxy, there's this big spherical part that we have to identify. We know it's there. That's called the halo, and it's made of dark matter. That was the first piece of observational evidence for dark matter, but since then, it's just all over the map. Millions of pieces. It works. It fits a lot of data. I'll tell you about a few more. Another one is lensing, which again stems back to Albert Einstein. And the basic thing is that mass bends light. So whatever the dark matter is, here I've got a massive compact halo object, but whatever it is, it doesn't give off light, but it bends the light from behind it. For example, if you have a star, then the light might bend in this direction. on the way to the telescope. There's no kink. It's just my poor drawing capabilities. And so you'd say, okay, well, actually, I've seen a star over here. But then you might notice, wait a minute, I see the same star over there because the light bent in the other direction. And you'd notice, but it's sheared. So you're seeing multiple images, and they're sheared. And in the ideal case, if everything's perfectly lined up, which is pretty rare, you would even see something called the Einstein ring, which first found by Jackie Hewitt at MIT. So on your phones, there's an app written by a Michigan grad student, Eli Reichoff, which has all the gravitational lensing equations properly put in there so you can lens yourself. So my student did that. Here he is. Getting more and more lenses, you put more stuff in the way. So going backwards from this, you can figure out what had to be put in to get it back to the original object, and that's what's done. So, but now I'm going to real data from Hubble Space Telescope. You have here a whole bunch of lensed objects, and I can't keep straight what's going on in there. But you can see right away there are sheared objects in there, and a lot of them. Starting from this picture, you can reconstruct the dark matter that acted on the background light and produced these images. I'm going to show you a plot that once that's done of what you would see, but I've taken the best pictures, and so this one does not correspond to the last one. It's a different object. But this is the mass distribution of a cluster of galaxies. So you see the galaxies themselves, and in between, you also see this dark matter. So there's more dark matter in between the galaxies. So this is a computer reconstruction of the mass that would produce those distorted images in the lensing taken from Hubble Space Telescope. Let me turn to a third type of approach for searching for dark matter that makes us believe that we know what's going on. This is an image called the bullet cluster. Called that because this pink thing is supposed to look like a bullet. We think what's going on here is that there are two clusters of galaxies. The two clusters are colliding with one another. And after the first collision, they went through each other, and eventually they'll merge together into a single one. But we caught this one right after the first collision. And you can see the behavior of two different types of matter that makes you think you really do know what's going on. This pink is supposed to represent X-ray emission. And so that is gas. So when you and I hit, we're not going very far. We get stuck. We have electromagnetic interactions. We have strong interactions. We're not going very far. And that's what happened to the gas. Dark matter, on the other hand, is essentially collisionless. I mean, hopefully not entirely, otherwise we'll never find it, but it just keeps going. And so in purple, there is additional mass out there, found again by lensing, and it behaved differently. So the idea is we see the differentiation between these two different types of materials. They both matter, but they're acting very differently. This makes us think we do know what's going on. I've talked about a number of ways that we know that dark matter exists. The rotation curves, gravitational lensing, the bullet cluster. And before I leave this subject, I want to talk about one more reason that dark matter has to be there. And that's because, and I'm going to say it's because we know we exist. If you had ordinary matter trying to clump together to make galaxies, you have a problem. Photons stream out. They just move out. So nothing would ever collapse. And the early universe was ionized, and so all that ionized matter would also stream out. You wouldn't be able to clump things. Galaxies wouldn't form rapidly enough for us to be able to exist yet. Dark matter, on the other hand, isn't tied to the photons. It doesn't have electromagnetic interactions. So dark matter can start to clump much earlier, and it makes the potential wells for the galaxies and so forth earlier, and then later on the atomic material falls in. So I'm going to show you a few slides from a computer simulation of how this would work, where the blue particles in here those are clumps of dark matter. There's no ordinary matter in this simulation. So you start with the dark matter not entirely uniformly spread out, almost, but not entirely. And those initial perturbations come from inflationary cosmology, as far as we know. So this is when the universe was 29 times, any length scale in the universe was 29 times shorter than it is now. You let the simulation move forward in time, and you're going to see the dark matter start to clump together more and more until you get to today. So this is, here today we would have these long filaments of structure, and galaxies would be at the nodes or intersections of these filaments. This simulation matches reality really well, and that's where that's also where we get the idea that we know what's going on, because it has that simulation matches this picture, this breakdown of components into different pieces. And for it to work, you need cold dark matter. All right, so now the question is, what is the dark matter made of? The first things you might try would be simple. It might be gas or rocks or dust, snowballs of hydrogen. But all of those have observational signatures that we don't see. So you have to go to something else. Now the next thing you might try is say, okay, so we don't have a lot of bright stars, but what if we have a lot of faint stars and we just need better telescopes? Or even if you go less than 0.1 of the mass of the sun, then you get sort of planetary objects that never had fusion, they never lit up, and you could have a lot of those. So those things fall into the category of MACHOS, massive compact halo objects. And at the time there was a debate between these, these things would be made of ordinary matter, before we knew that you couldn't really match everything with that. And then on the other hand, people were already saying, no, we've got to have something non-baryonic, and that forced people to exotica, such as these kinds of things. So you had the battle between the MACHOS and the WIMPs. And I worked on both sides of the debate. So I mentioned that in the MACHOS, it could have been these small stars, but through a combination of data and theory, we argue that, well, actually Hubble Space Telescope and other data showed this is only 3% of the galaxy. Then it's still possible that still are remnants, like especially white dwarfs. When the sun runs out of fuel, eventually it'll collapse down and become a white dwarf. So there could be a lot of those out there, and so we looked at that, and we argued that only 15% of the galaxy can be white dwarfs. So since then, there are microlensing experiments that really show that this is true, that you can't not. This is not enough to explain the dark matter, and everybody agrees now. 15% could be white dwarfs, but that's it. By the way, a stellar population worth looking for. All right, so baryonic dark matter is not enough, which takes us to exotica. The dark matter is not atomic, so what could it be? And here we have many candidates, and we hope that one of them is right. In particular, we try different types of, on the whole, different types of fundamental particles. So here's a list that people take seriously. Too bad it's not neutrinos. Neutrinos exist, but they have two problems. Already in the 80s, people knew it wasn't going to work because they're too light, and they stream out of things, and they also would ruin galaxy formation. And of course, now neutrinos are known to have small masses, 10 to the minus something eV. That means they're adding up to a fraction of a percent of the universe, not a quarter of it. There is a variant on neutrinos, though, sterile neutrinos. This is not not electron, muon, or tau neutrinos, but something else, that they don't have standard model interactions, and that's still an interesting possibility. In fact, they might have something to do with explaining the mass of the ordinary neutrinos. So there's some people argue about the data possibly showing hints of that. Now, the two candidates for dark matter that are, other than sterile neutrinos, that are taken the most seriously would be WIMPs and axions. And the reason is that both of those exist they're not invented just to solve the dark matter problem, but instead they're already there in particle physics for completely different reasons. So the axion, for example, arises as part of a solution, automatically exists as part of a solution to a problem in the theory of strong interactions. I'm not going to say a lot about axions today, other than to just say that it's kind of interesting because in the search for axions, it's really astrophysics and cosmology that bounds the remaining mass range, because up here, here's the axion mass on this axis right here. you would end up either with too much dark matter, or you would destroy stars because axions would pull the energy out of the stars. So you're left with this axion window in here, and people are looking for that. In particular, this is axion mass versus the interaction strength of axions, the coupling constant. And this yellow band is the theoretically preferred region based on the previous slide I showed you. So this is the ADMX experiment that's within the next few years really going to push into that region. And so that would be really exciting if axions were found. But I'm going to turn for most of the rest of the talk to the other very strong candidate for dark matter, and that would be WIMPs, or weakly interacting massive particles. So just so you know, there's billions going through your body every second. One a day or one a month hits one of your nuclei, and it's not knocking you over. It does not have strong interactions or electromagnetic interactions, but what WIMPs do have is they do have weak interactions, hence the name. Then they weigh between a GeV and 10 TeV, something like that. So that's what the name, that's the information encoded in the name. There's two reasons that people think these are really good candidates. The first one is that you get the right abundance of WIMPs. The only particle in physics ingredient we have here are weak interactions. Now let's look in the early universe, which is a thermal bath of particles hitting each other constantly. So we can compute how many photons there are, how many of everything there is. These particles are their own antimatter. You can watch them hit each other, annihilate, and this goes on until the universe expands enough and the WIMPs cannot find each other anymore. At that point, the number density remains constant, and you can figure out, the number remains constant, and you can figure out how many are left today. And when you do that, you get roughly the right abundance to explain the dark matter. So in particular, the fraction of the universe in WIMPs, that's what omega is, turns out to be, you get the right answer as long as the annihilation cross-section is set by weak interactions. So this is either a coincidence, or some people call it the WIMP miracle. The second reason that people think that WIMPs are good candidates is because they're already there in other theories. For example, supersymmetry at the electroweak scale. Every particle that we know, here are the quarks and photons and so on, each of these things gets a partner, a supersymmetric partner, and you get the twiddle over the top when you write it. So quarks become squarks and so on. These partners, they're heavier, which is why we haven't found them. And they would decay into ever lighter ones until you get to the very lightest one. That thing would be stable. And so this lightest supersymmetric particle might be the dark matter, and in fact, it would act like a WIMP.
One correction. There used to be an I here for Dimitri.
Oh, sorry, Dimitri. There's another theory where WIMPs automatically appear, and that's in universal theories of extra dimensions, where there are these particles, Kaluza-Klein particles, and which also have the same kind of behavior, but the lightest one would be also a WIMP. So that's another place in theory to look for WIMPs. So we've got very well motivated particles, and now somebody has to go and find them. Okay, so there's three ways that people do that, and I'll tell you about all three. This is the same Feynman diagram, which you shouldn't draw 3 times, but I did anyway, because you're supposed to read it in this case from left to right. So I'll start out here with producing dark matter particles at the LHC. Okay, so here's the LHC at CERN. I just recently found this picture, which I really like. So you've got the 17-mile ring accelerating protons in opposing directions and colliding them, and the relevant detectors where the collisions take place for what I'm talking about are CMS and ATLAS. Just some pictures. So this is Fabiola Gianotti, who was, she's now Director General of all of CERN, and the ATLAS detector. Here's a picture of ATLAS. Some guy standing there just to These are just amazing pictures, amazing collaborations. Peter Higgs in front of the CMS detector. So the first great discovery of the LHC was the discovery of the Higgs. There's this bump at 125 GeV. The second thing that they're looking for, of course they're looking for any new physics, but the second goal would be to find supersymmetry or to find dark matter. Or what would you see? Well, these two protons colliding might give rise to some supersymmetric particles coming out, which go through a chain, a decay chain, and so on, until you get to the lightest one, which could be the dark matter, and then that thing would escape detection. So you'd have some missing energy. The other thing you'd have is jets of particles coming from here. So far, nothing's been seen yet. What do we make of this? So this is actually not the most recent data, but it gives the idea. Supersymmetry. The minimal model has 105 free parameters. It's kind of hard to scan data for keeping all those in mind. But we can go down to having only 5. And the way you would do that is to say, what if, at some very high scale, all the fermion masses are the same, over here, and all the scalar masses are the same. That's this M0 over here. Then as time goes on, they change differently as a function of energy, so they run differently. But if you make that unification, you're down to 5 parameters, and that's what the experimenters have done here in this constrained minimal supersymmetric standard model to place bounds on these 2 parameters. In that case, you would have to be up here, above all of those lines, which means you're pushing masses up into the TeV scale. There's no discovery of supersymmetry below that. But I did want to make I guess my basic comment is that maybe things are at higher scales. You just have to build a higher energy collider. So I don't know where Peter is, but Peter's going to do that. Peter's going to build the next, in the sea. I love it. So we're going to go to 500 TeV in the sea, and then you're going to find it. And it's also possible that these simple models, these unified models, the way I've talked about them, are just too simplified, and you have to study, theoretically speaking, more complicated models. So even if you did discover something at the LHC, you would just know that it lived long enough to escape the LHC. You still haven't proved it's dark matter, although they're not talking about building tanks just outside the LHC to test the decay. But anyway, the ideal thing would be, let's take a complementary tack. Let's take advantage of all these WIMPs that are in our galaxy and build a detector that sits there waiting to be hit by a WIMP. So in here you would have some nucleus. The WIMP would elastically scatter off of it, and you would look for the tiny energy deposit when that happened. Now, these are really difficult experiments because you're talking about tiny count rates and really small energy deposits, KeV types of energy deposits. And, geez, I'm running really late already. This is terrible. But anyway, so I have to tell you anyway. So this guy got me into dark matter. He's Polish, but he speaks English, French, German, and Polish all at the same time. So I met him at a conference in Israel where he knew where to go for the New Year's party. He started telling me about a paper that he was writing with Leo Sadolsky, which was looking for neutrinos by elastic scattering off of nuclei. And I'm going to start skipping pictures. These guys were the first to apply to WIMPs, Goodman and Witten. We wrote the next paper on this. I brought Andre up to Harvard, where the 3 of us, this is David Spergel. So we did some simple calculations. I did Feynman diagrams, and David put in the WIMPs in the halo of the galaxy, and we convinced experimenters to start building experiments. The event rate is number density times cross-section times velocity, as usual. You can split this into 2 pieces, the particle physics piece and the astrophysics piece, where this is the distribution of WIMPs in the halo, and this is the particle physics. People frequently talk about 2 possible scattering types. One is spin independent, where the scattering depends on the mass of the nucleus squared, coherent scattering. The other is spin dependent, where the scattering depends on the spin of the nucleus. As far as the distribution of WIMPs in the halo, we took them to be Maxwellian. where the typical particle speed is a few hundred, 270 kilometers per second. We thought this was a sort of shitty approximation, and people worked da-da-da-da. Actually, turns out it's really good. So we were lucky there, but anyway. So, but to do this, you have to go underground. You have to go, for example, this is in South Dakota in the Sanford mine. It used to be a gold mine. These are part of the Lux detector. And the next generation is going to be Lux Zeppelin. That's going to keep taking data. It's a worldwide effort. And I want to say a few words about what's going on with this DAMA experiment, because it's the only one that has positive signal. So what are they seeing? Well, the sun moves around the center of the galaxy. Okay, so I'm the sun moving around the center of the galaxy. WIMPs are moving in every which way, so I see them coming at me as a wind. Okay, so there's a wind coming at you. But the Earth also moves around the sun, so that means that the relative velocity between us and the WIMPs changes with the time of year. You'd expect a maximum count rate in June and a minimum in December. And this is what DAMA sees. I mean, the black curve is what you'd expect. And their data over 10 years see exactly the right annual modulation. It is a 9 sigma effect. Okay, have WIMPs been discovered? Well, that's a good question. So there's two issues. The first one is sociology, which is they won't release their data. And on their webpage, they have this bizarre quote from Rudyard Kipling. Yeah. Okay. And then the other problem is they're the only ones who've seen anything, and a lot of the other experiments have null results. All right, I can't resist this one. So Juan Collier, leader of Cogent, Rita Bernabe, leader of DAMA, Eleanor Prelay as a principal investigator of Xenon. I'm a Spaniard caught between two Italian women. These are definitely very strong personalities. And yes, their results are differing. So, but I don't know how to compare DAMA, which is made of sodium iodide, with Xenon, which is made of xenon. All right, so here's the WIMP mass, and here's the cross-section. If I make that assumption that the cross-section scales as atomic mass squared, then I can put everything on one plot. Then you have these green blobs are what it would take to explain DAMA. And this one here at 10 GeV is the particularly interesting one. But these negative results mean you'd have to be below the red and green curves. This is an out-of-date picture. A lot of stuff is not on here, but you get the point, which is, does that mean DAMA's ruled out? Well, no, because they're made of different materials, first of all. And second of all, people argue like mad, what's going on at threshold? Can we trust these results? So I'm going to, okay, just some fun pictures at meetings. The UCLA Dark Matter meeting, this is my favorite. This is the one that David Klein organized. Unfortunately, he died, but we're going to continue these in his honor and for ourselves. These are absolutely the best meetings ever. But so here's an update on what's coming. Okay, so super CDMS is really going to push to lower masses, and that's going to really help. It's made of germanium. Then as you go lower and lower sensitivity, this is called the neutrino floor, because you're going to start seeing neutrinos. And people here have done the best work on trying to figure out how can you go below the neutrino floor on the theory side. And then I did want to show super CDMS over here. There's a major collaboration here. I got to see some of the labs today. That was really cool. And so here are the people leading the different groups here. So thank you for showing me that. That was really awesome. And this, and I like this because these are these hockey puck shaped chips. They're about this big that the detector is made of, and that's the design of that. But if you really want to know what happened with DAMA, you're going to have to build something with the same material, these same crystals, and that is happening. There's 3 groups doing that. So one is Frank Kellerprice at Princeton started this SABRE experiment with in a mine in Australia. Also, the second group, cosine 100, and the third group, Anais. They're building crystals, and some of those crystals are really good. We'll know within 5 years whether DAMA is dead or not. In the long run, I won't say a lot more about that, except that we have to get people to agree to get the same answers. Now another major step forward will be directional capability, because imagine I could count how many WIMPs are coming from this direction compared to in that direction, 10 times more in the direction of the wind. That's a huge discrimination power, okay? That would be really, really amazing. Or you see diurnal modulation, the daily count rate changes also. If you saw that, then you'd really know what was going on. So I can't resist one slide on an idea that we had for how to do that. Yes, this is the same Andre Druckier who went off into biology for 20 years and came back saying, come on, let's use DNA. So the idea here is, by the way, this picture, this thing I've drawn here, you can buy that from off the shelf. What's the name of the company? Anyway, I'll tell you later. But so this is gold, nanometer thin plate of gold with a bunch of DNA strands attached, like we're going to have 10 to the 60 of them. And it's going to have to be a lot cleaner than the ones you buy from this company. But the idea is the WIMP hits the gold and knocks a gold atom forward into the DNA. WIMPs are not going to break your DNA, but the gold will. Now, once it does, these strands fall down, you collect the strands, and you analyze them. You make 1 billion copies with polymerase chain reaction, and then you gene sequence to figure out where the break happened. Now, the nice thing is you can control. This is A, C, G, da-da-da-da. So you can figure out where the break happened. And we're talking nanometer accuracy because that's the distance between the bases. So it's a nanometer tracker. Ask me about another idea, nanobooms, which I don't have time to talk about, because I do have to talk about the third approach to looking for WIMPs, which is called indirect detection. You're looking for messengers of the WIMPs. If you have 2 dark matter particles annihilate, they might turn into a pair of W's, and so on and so forth. And in the end, the 3 things you can look for are neutrinos, gamma rays, and positrons. And sure enough, there are experiments looking for all 3 of those. Ice cube, which is deep underneath the ice at the South Pole, looking for neutrinos. The many experiments, the most recent, the AMS, aboard the International Space Station, does have positrons. And Sam Ting, the leader of that, at some point was claiming that he'd found that this was due to dark matter, but nobody really believes that. So I have lots of slides about that, but it's probably just pulsars or something else. Seriously. And so actually this paper ruled out almost everything. These are some of my favorite people, ask me later. And they looked channel by channel at what would it take to produce the positrons we see. So you might have annihilation into BB bar, which would then give you positrons. That's this example here. So this is mass versus cross-section, annihilation cross-section in this case. To explain AMS, you'd have to be here. But if you're making positrons, you'll also make photons. And the Fermi telescope, the Fermi satellite, should have seen those positrons from the dwarf galaxies, and it hasn't. So you have to be below the blue line. So it's using a combination of different pieces to show that it just doesn't work. So they did this channel by channel and showed it doesn't work. There's other arguments for why it doesn't work, but let me go on. So here's the ice cube looking for neutrinos. The other interesting result at the moment, ice cube hasn't found anything yet, but we hope we'll hear from them. But there are results for gamma rays from the Fermi satellite. And the question is there anything from dark matter annihilation here? The Fermi looks at the gamma ray sky. So here's the plane of the Milky Way. So first of all, they found these giant bubbles. They're 50 light years in extent. That's kind of cool. What did I say? Oh, 50,000. Sorry, did I say 50? Yeah, I said 50. 50,000! Okay, that's a little different. Yeah, 50,000 light years in extent. Giants. And right at the center is a spherical region where they see a lot of gamma rays that could be from dark matter annihilation. So there's a lot of interest in that, in this gamma ray excess from the center of the galaxy. It could also be, again, pulsars. It could be point sources of some type. It could be pulsars. So I'm going to skip a lot of this other stuff. Should I or not? I don't know. I don't want to run out of time. I guess I should say that another place you look for gamma rays from is dwarf galaxies. Here's the Milky Way, and we have all these these dwarfs around us. Dwarfs are really, really dark matter rich. So they really should be producing gamma rays from the dark matter annihilation. And that's a very powerful way to get bounds. And that's ongoing. I think I better move on. Okay, so what is the status? Direct detection, DAMA has something. I do want to say on the annual modulation, there is not one alternate explanation remaining for the annual modulation. People thought it could be radon, it could be atmospheric muons, it could be a lot of things, and they really showed it's none of those things. So that's what's weird about it. There really is no other explanation. And it was Frank Calaprice he's at Princeton, and he was doing T violation experiments, precision measurements, and he said, we've got to go test this. That got my attention. So it is interesting. And here on the indirect detection side, the Fermi gamma ray excess near the galactic center, that's the other thing that might be from the dark matter annihilation. And on the theory side, we try to figure out what's going on. These two could be consistent with one another. But in the end, you have to have compatible signals in a wide variety of detectors, and you have to have all these people agree. I do want to talk about another subject, which is dark stars. This is sort of my latest baby that I've been working on, which you actually could treat as a way to look for WIMPs. The basic idea here is that the very first stars to exist in the universe, when it was about a few 100 million years old, those stars would be made almost entirely of stuff from the Big Bang, so they'd be made of hydrogen, a little bit of helium, but there would be enough dark matter around to power them. So that same dark matter annihilation could serve as the power source for these things. And all of this would predate fusion. So they'd be a new type of object and very early on. And I do have to show this slide. And so it was Doug Spoliar, Paulo Gondola, and I who originally had this idea. And I really only have one slide on it, but people who want to talk to me about it later, that would be great. So as I mentioned, these things they're really made of atomic matter, but they're powered by dark matter. The way this works is that inside an early protogalaxy, you have a collapsing cloud of hydrogen smack in the middle where you have a lot of dark matter. And as that cloud is collapsing, trying to make a star, the dark matter annihilation products eventually get trapped inside, and they thermalize that collapsing cloud of hydrogen, and it becomes a star. It's in thermal equilibrium, hydrostatic equilibrium, and they can grow to be very big. They can grow to be, not all of them, but some might end up 10 million times the mass of the sun, 10 billion times as bright as the sun. Now you've got something that you could look for in the James Webb Space Telescope that's launching next year. And there are people here that I'm talking to about that because I would be really, really excited if you could find these. And one of the signatures might be that since they're stars, they pulsate. So that they would look different from other early objects, like early galaxies. Well, what happens once these things run out of fuel? Well, eventually they'll leave this nice dark matter-rich region, and then they'll turn eventually into black holes. They'll collapse into black holes, and that would be really nice if you had big seeds to explain the very many supermassive black holes that exist in the universe. There's even a 10 billion solar mass one at a redshift of 6. So these are nice seeds for those objects. So I've talked about different ways to look for dark matter, and let's hope it happens soon. I did want to mention, as I started out saying at the beginning, that there's some possible evidence of maybe a 7 keV sterile neutrino. There's a 3.5 keV line. This is X-ray data that's seen in a number of places. It's seen in clusters of galaxies. So it's seen in some places, but then other people say, no, it's not seen here, da-da-da-da-da. There's a lot of argument going on, even to the point where you hear one speaker saying it's ruled out, and then the next one mocking the previous speaker. And I'm staying out of this one, but it's very intriguing. the stereo neutrinos of this mass are also very, very hard to make. It's hard to produce them. It's hard to understand them. They're certainly not thermal particles. There's different mechanisms people look at. So I guess I just wanted to repeat the story here. So on the WIMPs, there's some evidence there. There's this 3.5 keV X-ray line that might be from 7 keV neutrinos. And then there's a 511 keV line also that I really am not going to talk about much, which could be due to MEV dark matter. So that's sort of what's hot in the experimental side. I haven't said anything about the big beast, dark energy, the 70%. The only thing we know about it is it's not matter. Matter makes things clump. Whatever this is, it's causing galaxies to accelerate from one another. So not just expand, but accelerate from one another. And one of the key people that played a role in this major, major discovery is Nick Sunset. I am not going to speculate about what it's made of. I think this is a really, really, really tough problem, and we're probably all barking up the wrong tree at this point. On the data side, we will be able to determine, is it constant in time or changing in time, this contribution to the total energy density. And I'm certainly able to end with a joke. All right, so this was at the World Science Festival in New York. The three of us were talking about dark matter. That's me, Eleanor Prelay, Glennis Farrar. These three guys about dark energy, Mike Turner, Sol Perlmutter, and Brian Greene. And I made a true statement. And all of the stuff I've talked about is, Roland or who was mentioning this, I'm not sure, but this is the book that they were talking about, the Cosmic Cocktail 3 Parts Dark Matter. So if you want to read this at a simple level, then go take a look. So I think I'll end there. I mean, what kind of WIMP does it take to make it work? So the amount of the dark stars are contributing nothing to the overall mass budget of the universe. They're irrelevant. So I don't know if that's what you're asking, but they play no role whatsoever in this picture, like the pie picture. They don't count. There's enough of them maybe to find some, but they're irrelevant in the grand scheme of the mass and energy content of the universe. They're irrelevant. Okay, if we were able to detect the what? God, I'm not hearing. If we can, the W boson's been detected, yes?
Yeah, but if it's possible to detect it after that, is it to detect it weakly as
I don't know how to answer that. I'm not sure I understand the question.
Anybody understand the question?
You mean looking for, you mean annihilation into W pairs, W plus minus? Okay, so annihilation into W's, the W's are going to turn into other things. So you're not going to detect the W's. You're going to detect the W's that turn into eventually positrons or whatever. But, I mean, so certainly people study the channel, the annihilation into the W plus W minus channel. People study that, and then they ask, okay, what would I get out in terms of positrons? What would I get out in terms of photons and so forth? So you would detect things farther down the line, but you would reconstruct, yes, exactly that channel. Yes, people do that. Mm-hmm. Sorry, I just can't hear very well.
The dark stars is very intriguing idea, but my question is, what is the end result of that star? How we can describe
Yeah, yeah. So black holes. Well, so the initial dark star, when it takes over this cloud of molecular hydrogen, will be maybe 1 solar mass or whatever, something like that. But then it accretes. More and more mass falls onto it. The dark stars are really weird. They're in the size of these things. They're giant puffy objects. So the radius is 10 times the distance between the Earth and the Sun, so 10 AU. And there's no fusion, no hot. It's not hot. Dark matter annihilation spread out uniformly, and the surface is cool, so it just keeps accreting. So as long as you have dark matter power, then there's nothing to stop more and more accretion. There's no feedback from hot stuff coming off. But exactly predicting how many of what mass is very difficult because we don't know that they form inside a million solar mass halo of dark matter. That thing merges with other mini halos and so on. So the cosmology of how the dark matter form structure becomes important, and then exactly where this object moves with the mini halo and so on. So I don't know how many of what mass we get. But we did, so the PIs on the James Webb, John Gardner and John Mather, they really like our dark stars because they're big enough they could see them. And they wanted us to predict how many would they see. So it's sort of like what you're asking. And so the first thing we did was get spectra. So we can do that, okay? And then we asked Paul Shapiro to help with how many mini halos would you get. And so you would get a peak at around a redshift of 12. Everything peaks at a redshift of 12. And so then we said, okay, given that, we can parameterize by some little f. How many of those have dark stars in there? And then you guess, okay, if they were this big, and so on. So we don't know. It's tied into the cosmology of what the dark matter is doing. So the initial mass function of the first stars might actually be determined by where the dark matter is going. That's kind of fun.
How does this dark star cloud get rid of the single cloud in order to locate them in the solar system in the planets? Otherwise, the sun would be formed. So if you have a cloud that's single with forming, it has a little bit of rotation. How do you limit that rotation?
Well, I think the answer to that is I remember discussing this with Simon White, and the things are big, so there's not much angular momentum. Not important. And because for the same reason, general relativistic instabilities are not there. R is big. Oh yeah. The sun is not at the center of the galaxy, so the amount of dark matter here is not enough to power the sun. It's possible that near the center of the galaxy, in particular, there might be white dwarfs. People call those WIMP burners that would be powered by dark matter annihilation. So in principle, it's possible. Now there are other factors. The other one is that our sun is powered. We have the carbon nitrogen, the CNO cycle and the PP cycle and all that. That's a very potent heat source. And so we've got a lot of other stuff going on now. So it's not as simple as these early molecular hydrogen cooling picture. So there's more chemistry. The chemistry is more complicated now. Now in the sun, if you have scattering of WIMPs as they go through the sun or the Earth, then you would capture the WIMPs. They would sink to the center of the sun or Earth, annihilate, and you can look for those annihilation products. So people at IceCube are looking for annihilation. They're looking towards the sun in particular, more than for the Earth, looking for the annihilation products. So there could be some down there in the core of the Earth even. But our local dark matter density is not high enough to have a power source. Of the Queen of Sweden? That's kind of a long story. Okay, so you know how there's no Nobel Prize in astronomy. So there was a guy named Crawford, who is a Swedish industrialist, who decided to give the Crawford Prize in astronomy instead. And it's every 3 years. It alternates with math and other fields. And so it was given to people's Gunn, and Reese. And they had a conference going along with it, and I was invited to the conference. So I went there, and we had this dinner in this wonderful mirror hall, which is imitation Versailles and so on. And at my table was the granddaughter of Mr. Crawford. And so I started taking pictures. I took a picture successfully of the king, and I tried to take a picture of the queen, but I got a potted plant. So then later after dinner, she introduced me to her brother, who wanted pictures of himself with Lisha Verde. And so I took a picture, and I cut their heads off. So he wanted the pictures. He's like, what are you doing? And he saw the picture of the queen. He goes, come on. So he takes me over and introduces me to the queen. And she says, well, there's more funny stuff on the way, but I'll go try to get to the point. So she says, please explain to me what is space. Oh, Jesus. So I started going on about, I'm like, you're getting kind of nervous, right? And you're thinking, okay, outer space. And I try to explain, you leave the Earth and you leave the solar system, you keep going, da-da-da-da, and then you get to 10 to the minus 29 grams per cubic centimeter. And she looks at me like utterly puzzled and says, that's not what the mathematician said. I'm like, oh, Jesus, oh God, she's asking about space-time or something, right? And I didn't know, and I don't know, I didn't know what to say, and the conversation stopped. And then you know how you go, oh my God, I got to say something. So I said, oh, are you best friends with the Queen of Norway? That was her job, always to smile, no matter what, right? And she went, I'm like, so I ran away at that point. Now, what I didn't know, this was the 100-year anniversary of the secession of Norway from Sweden. That day, okay? So she probably thought I was baiting her or something. I had no, and by the way, Norway got the oil, right? So that was a big mistake. But anyway, there's only one country in the world more expensive than Sweden, and that's Norway. It is the most expensive country. I think it's even more expensive than the Arab countries. Yeah. Okay, so I hope you think that story was worth it. I don't know.